The most valuable company in the history of the stock market just walked into quantum computing's most contested battlefield and refused to pick a side. And that refusal might be the smartest, most dangerous move any of them have made yet. To understand why this genuinely qualifies as a hardware war, and not simply another round of exciting but ultimately forgettable tech announcements, you first have to understand something most coverage of quantum computing glosses over entirely. This isn't one race with one finish line, it's at least 4 separate races, running simultaneously using 4 fundamentally incompatible kinds of physics. And as of 2026, nobody, not the companies involved, not the independent scientists studying them, not the governments funding them, actually knows which one wins. IBM and Google have both built their entire quantum programs around superconducting circuits, tiny loops of metal cooled to temperatures colder than deep space. IonQ and Quantinuum have gone in a completely different direction, trapping individual charged atoms in place using precisely tuned lasers, an approach called trapped ions. And Microsoft, in what may be the single riskiest bet in this entire story, chose neither path. It bet everything on a particle that has never been directly observed by anyone anywhere, under any circumstances. This is not chaos. This is 4 separate, genuinely credible technology companies, each backed by billions of dollars, each staffed by some of the most brilliant physicists and engineers alive today, looking at the exact same problem and arriving at 4 entirely different conclusions about how to solve it. What makes 2026 specifically the year this quiet technical disagreement finally erupted into something that actually deserves to be called a war is a specific industry-wide convergence that quantum analysts have been watching build for months. According to detailed 2026 industry analysis, what makes this year the most important in quantum computing's history isn't any single breakthrough, it's the convergence itself. Hardware across nearly every competing approach has started advancing faster than the error correction techniques originally designed to manage it. Cloud access has genuinely democratized experimentation, letting smaller startups and university labs actually test quantum hardware without needing to build their own multi-million-dollar facility. And critically, DARPA's own quantum benchmarking initiative has started imposing independent, government-verified scrutiny on roadmap claims that, for years, companies had simply been allowed to make publicly without any serious outside verification at all. Think about what that specific combination of forces actually creates. For the first time, every competing company's boldest promises are being checked against the same independent yardstick at the exact same moment that raw hardware progress across the entire industry has started accelerating past what anyone expected just a year or 2 earlier. That's precisely the kind of pressure that turns a quiet, polite technical disagreement into an open public war. Let's start with the company that chose the strangest, riskiest path of all, because understanding Microsoft's specific bet reveals just how much genuine scientific uncertainty still sits underneath even the most confident corporate press releases in this entire industry. Rather than adopting superconducting circuits, trapped ions, or any of the qubit technologies favored by its competitors, Microsoft built its entire quantum program around something called a topological core architecture, betting that a genuinely different category of particle, one that exists only inside carefully engineered materials, cooled to extreme temperatures, could solve the error correction problem at the level of raw physics itself, rather than requiring layers of complicated software and hardware built on top of noisier, more conventional qubits. This is, in every meaningful sense, a physics-first strategy, an attempt to make the underlying hardware inherently, structurally more stable, rather than accepting instability as an unavoidable cost of doing business and trying to manage it after the fact. Zulfi Alam, Microsoft's corporate vice president of quantum, described the company's broader infrastructure ambition in a genuinely striking, physically vivid way, explaining that Microsoft envisions its quantum hardware sitting right next to a hyperscaler, meaning physically co-located with the exact same massive cloud data centers already running Microsoft's ordinary classical computing business. Picture what that actually implies for the future: quantum processors, built around genuinely unproven physics, sitting in the same building as the servers currently running your email and your cloud storage, close enough that Microsoft imagines connecting them almost seamlessly. But here's where this specific bet earns its reputation as the highest risk strategy currently being pursued by any major company in this entire industry. And honest coverage of this story demands confronting that risk directly rather than glossing over it. Winfried Hensinger, a physicist at the University of Sussex with no financial stake whatsoever in Microsoft's success or failure, offered a genuinely blunt, independent assessment when speaking with the respected publication, Physics World. Topological quantum computing, in his professional judgment, is probably 20 to 30 years behind the other platforms. Read that again and sit with exactly what that specific number implies. Not a few years behind. 2 to 3 full decades behind competitors like IBM and Google, according to an outside expert with genuine scientific credibility and no reason to flatter or attack any particular company. This assessment lines up directly with concerns raised by other independent physicists, examining Microsoft's specific published results, questions about whether the underlying particle Microsoft's entire architecture depends on, something called a Majorana zero mode, has actually been definitively proven to exist inside Microsoft's own hardware at all, or whether the company's published data remains genuinely open to alternative explanations. This is the deepest, most consequential uncertainty sitting inside the entire quantum hardware war. Microsoft isn't simply betting on which engineering approach will scale most efficiently. It's betting that a specific, still scientifically contested piece of fundamental physics genuinely works the way its own research team believes it does, and if that foundational bet turns out to be wrong, everything built on top of it collapses along with it. IBM's strategy sits at almost the exact opposite end of the risk spectrum, and understanding why requires appreciating just how deliberately, almost stubbornly conservative the company's entire approach has been. Rather than chasing an exotic, unproven category of physics, IBM committed early to superconducting qubits, the same broad technological family Google also uses, and the single most common, most experimentally validated qubit type currently deployed anywhere across the entire industry. IBM has shipped quantum processors according to a consistent, publicly tracked roadmap continuously since 2020, an unusually long, unusually stable track record in an industry that has otherwise been defined by dramatic pivots, retracted claims, and shifting timelines. The company's stated strategy unfolds across 3 distinct, carefully sequenced phases: utility-scale quantum computing, targeted for 2024 through 2025, fault-tolerant systems targeted for 2026 through 2029, and what IBM calls quantum-centric supercomputing, a genuinely integrated fusion of quantum and classical computing infrastructure, targeted for 2030 and beyond. IBM's roadmap specifically points toward reaching 100,000 qubits by 2030, an extraordinarily ambitious number even by this industry's own inflated standards. And unlike Microsoft's comparatively isolated physics-first bet, IBM has spent years deliberately building out an enormous surrounding ecosystem, the IBM Quantum Network, now encompassing more than 200 separate academic institutions, government laboratories, and Fortune 500 companies, all building experience and expertise directly on top of IBM's specific hardware platform. Think about the strategic logic embedded inside that specific choice. IBM isn't betting primarily on having the single best underlying physics. It's betting on patient, methodical, proven engineering, combined with an ecosystem so deeply entrenched that switching to a competitor's platform becomes genuinely costly and disruptive for any organization that has already invested years building expertise on IBM's specific systems. And then there's NVIDIA, whose entry into this specific hardware war looks almost nothing like either Microsoft's or IBM's strategy. And understanding exactly why reveals what might be the single most interesting, most strategically unusual move happening anywhere across this entire competitive landscape right now. NVIDIA isn't building a quantum chip at all. It has made no bet whatsoever on superconducting circuits, trapped ions, neutral atoms, or Microsoft's contested topological particles. Instead, according to detailed comparative analysis published by Quartz in the spring of 2026, NVIDIA is positioning itself as something structurally different from every other player in this race, a hardware-agnostic open software layer capable of integrating across essentially every competing qubit platform simultaneously, regardless of which specific technology ultimately proves victorious. This is precisely the strategy embodied inside NVIDIA's Ising models, the AI system covered extensively in previous coverage on this channel, designed specifically to handle the calibration and error correction workloads every single quantum hardware company, regardless of their underlying technology, ultimately has to solve in exactly the same fundamental way. Here's the detail that separates NVIDIA's specific strategy from a simple, generous act of industry goodwill, though, and honest coverage demands drawing this distinction clearly. Quartz's own reporting includes a genuinely sharp, important observation about exactly how NVIDIA's ecosystem actually works underneath its open, welcoming surface. Ising's models are open source, the analysis explains, but the stack they run on is not. The decoder requires NVQLink's low-latency interconnect, the calibration workflows run through CUDA-Q, and the deployment tooling targets NVIDIA hardware. Read that carefully because it reveals precisely how this specific strategy actually functions in practice. NVIDIA genuinely doesn't care which specific qubit technology ultimately wins this broader hardware war, superconducting, trapped ion, neutral atom, or even, eventually, Microsoft's contested topological approach, if it somehow proves out. But every single one of those competing technologies, if they want to actually use NVIDIA's genuinely superior software for calibration and error correction, has to run that software on NVIDIA's own GPUs, through NVIDIA's own interconnect, using NVIDIA's own software platform. This is precisely the same underlying business logic that made NVIDIA the dominant, indispensable force behind the entire artificial intelligence boom in the first place. And it's being deliberately, methodically redeployed here, inside an entirely different, still-forming industry. Quartz's own analysis states this connection directly. The business logic mirrors NVIDIA's broader playbook. Pass inte gibse. Consider, too, that this specific quantum strategy wasn't a sudden, reactive decision made once NVIDIA noticed competitors gaining momentum. According to detailed industry analysis published in April of 2026, NVIDIA made investments spanning 3 entirely separate qubit modalities within a single week in September of 2025, months before NVQLink's public launch, and more than half a year before Ising's own public release. Think about what that specific timing reveals. While Microsoft was publicly betting its entire quantum program on one contested particle, and IBM was publicly committing to one proven but comparatively slower-moving qubit technology, NVIDIA was quietly, deliberately spreading its own bets across multiple competing approaches simultaneously, months before the broader industry had any idea just how seriously the company intended to enter this specific hardware war. According to the same analysis, this pattern signals that NVIDIA, described as the world's most strategically prescient hardware company, recognized the industry's genuine inflection point months before most outside observers did. The evidence that this strategy is actually working, rather than remaining purely theoretical, shows up clearly in the specific name partnerships NVIDIA has assembled across nearly every corner of the competing quantum hardware landscape. Consider Rigetti Computing, a company building quantum hardware in the same broad superconducting qubit family as IBM and Google, technically NVIDIA's own supposed rivals in the pure hardware sense. According to detailed 2026 stock market analysis, Rigetti has forged what the report specifically describes as a deep partnership with NVIDIA, aiming to integrate Rigetti's own quantum hardware directly with NVIDIA's GPU-accelerated classical computing clusters, an approach the same analysis calls widely considered the most realistic path to near-term quantum advantage, currently available anywhere in the industry. Think about the genuine strangeness of that specific arrangement. Rigetti is, in the pure sense of competing for quantum hardware dominance, a rival to IBM and Google. But when it comes to the classical computing infrastructure surrounding that hardware, Rigetti has chosen to build directly on top of NVIDIA's ecosystem rather than developing its own competing solution from scratch. This is happening far beyond a single American startup, too. According to industry coverage from June of 2026, both Germany and Japan have implemented NVIDIA's quantum software platform directly inside their own national quantum technology initiatives, meaning entire sovereign governments, not just individual private companies, are choosing to build their national quantum computing strategies on top of infrastructure NVIDIA controls. The breadth of this specific ecosystem extends into corners of the technology industry that have nothing, obviously, to do with quantum computing on the surface. And that breadth itself tells you something important about how deliberately, how comprehensively, NVIDIA is embedding itself across this entire emerging industry. In Poland, the Poznan Supercomputing and Networking Center partnered with a quantum hardware company called Orca Computing, and with NVIDIA directly, specifically to accelerate the development of hybrid quantum classical high-performance computing systems. An Israeli quantum computing startup called Classic teamed up with both NVIDIA and the German automotive manufacturer BMW Group, applying quantum algorithms combined with NVIDIA's GPU accelerated simulation technology to optimize the physical architecture of electric vehicle mechatronic systems, a genuinely concrete, industrial application connecting quantum computing directly to a product real consumers might eventually drive. Think about the strategic pattern emerging across all of these separate, seemingly unrelated partnerships. National governments in Germany and Japan, a Polish supercomputing center working alongside a British quantum startup, an Israeli company partnering with a German car manufacturer. None of these organizations are competing directly with each other in any meaningful sense, but every single one of them has chosen independently to route at least part of their quantum computing strategy directly through NVIDIA's specific software and hardware ecosystem, precisely the kind of broad, distributed infrastructure dominance that made NVIDIA's earlier conquest of the artificial intelligence industry so difficult for any single rival to challenge directly. This is where the deeper, more genuinely fascinating strategic insight buried inside this entire hardware war finally comes into full focus, because it reveals something Microsoft and IBM, for all their genuine scientific and engineering strength, structurally cannot replicate no matter how hard they try. where IBM and Google have each explored using artificial intelligence internally to help manage their own quantum error correction. According to reporting from the technology publication NVQLink, those specific internal efforts remain tied exclusively to each company's own proprietary hardware. Google's internal AI tools for managing Willow's error correction help Google's own chip. IBM's internal machine learning research helps IBM's own superconducting processors. Neither company's internal AI investment crosses over to help a competitor's hardware, because doing so would directly undermine each company's own core competitive strategy, built specifically around convincing customers their particular qubit technology deserves exclusive commitment. NVIDIA faces no such structural conflict at all, precisely because NVIDIA isn't trying to convince anyone that any specific qubit technology deserves exclusive commitment. It's betting, quite explicitly, that it genuinely doesn't matter which specific qubit technology customers ultimately choose, as long as whichever one they pick eventually needs to run through NVIDIA's own classical computing infrastructure to actually function at scale. Zoom out from any single company's specific strategy for a moment and consider what this entire genuinely unresolved competitive landscape actually reveals about where quantum computing stands right now in the middle of 2026, according to detailed comparative hardware analysis published this year, examining IBM's superconducting approach alongside Google's own superconducting systems, IonQ's trapped ion technology, and Quantinuum's competing trapped ion platform. Each of these four companies uses different technical metrics, different marketing language, and fundamentally different underlying physics, making direct apples-to-apples comparison genuinely, honestly difficult, even for serious industry analysts working full-time to track this space. IonQ's trapped ion approach, for instance, offers genuinely remarkable qubit quality by certain measures, including what's called all-to-all connectivity, meaning any single qubit inside the system can directly interact with any other qubit, alongside coherence times measured in full seconds, rather than the mere microseconds typical of superconducting approaches like IBM's and Google's. But that same trapped ion approach pays a real measurable price for those advantages, with individual quantum operations running considerably slower, roughly 1 full millisecond for a basic 2-qubit gate, compared to the dramatically faster operational speeds superconducting systems typically achieve. Meanwhile, Quantinuum, pursuing its own competing trapped ion strategy, achieved what recent industry coverage describes as an 800-fold improvement in fault tolerance, specifically through logical qubits, developed in partnership with Microsoft, an interesting detail revealing that even companies pursuing genuinely different core qubit technologies sometimes find themselves collaborating on specific, narrower technical challenges, even while remaining broader competitors across the industry as a whole. So who actually wins this genuinely unresolved hardware war? The honest, carefully researched answer, the kind this channel has consistently tried to provide across every previous story exploring this rapidly evolving industry, is that nobody currently knows, and anyone claiming genuine certainty right now is almost certainly overselling their own confidence. Microsoft's physics-first bet on topological qubits could, if the underlying science genuinely holds up against the serious scientific skepticism currently surrounding it, eventually deliver a qubit so inherently structurally stable that it leapfrogs every single one of its more conventional competitors, exactly as the company's most confident internal projections suggest. Or it could, exactly as independent physicist Winfried Hensinger's blunt assessment implies, remain 20 to 30 years behind the rest of the industry, a fascinating scientific dead end that never manages to fully validate the fundamental physics its entire architecture depends on. IBM's patient, methodical, proven approach could steadily, reliably grind its way toward genuine fault tolerance exactly on the timeline the company has consistently, publicly committed to since 2020, rewarding its enormous surrounding ecosystem of institutional partners with exactly the kind of dependable, incremental progress that ecosystem was specifically built to support. Or it could find itself technologically outpaced by a rival's sudden and unexpected breakthrough, exactly the kind of disruption that has repeatedly upended supposedly settled technology races throughout history. And NVIDIA's genuinely clever hardware-agnostic strategy could prove to be the single smartest bet of the entire hardware war, positioning the company to profit substantially regardless of which specific qubit technology ultimately wins, exactly as its own earlier, wildly successful strategy inside the artificial intelligence industry already demonstrated works remarkably well in practice. Or, alternatively, once one specific qubit technology finally decisively pulls ahead of its rivals, that winning company might find it genuinely doesn't need NVIDIA's software layer at all anymore, having built its own internal alternative once its underlying success finally justified the investment required to do so. What makes this specific moment in quantum computing history genuinely worth your continued attention isn't any single company's individual strategy in isolation. It's the fact that three fundamentally different, genuinely credible theories about how to win an entire emerging technology industry are all currently being tested simultaneously in public, with billions upon billions of real dollars, real scientific reputations, and real verifiable dated technical benchmarks, all riding directly on the outcome. Microsoft is betting that owning the deepest, most fundamental physics eventually wins every technology race, no matter how long that particular bet takes to pay off. IBM is betting that patient, methodical, proven engineering, combined with deep ecosystem lock-in, ultimately outlasts flashier, riskier competitors, chasing more exotic, less proven approaches. And NVIDIA is betting quite explicitly that in a genuinely fragmented industry where nobody can yet confidently predict which specific hardware technology will eventually win, the single smartest, safest strategy is refusing to place that particular bet at all, and instead building the essential software infrastructure every single competitor, regardless of which one ultimately wins, will inevitably need in order to actually function. If you want to understand exactly which one of these three genuinely competing theories about winning this hardware war eventually proves correct, and what happens once DARPA's independent verification efforts finally force each of these companies' boldest, most confident claims to withstand genuinely rigorous, government-backed scrutiny, that's precisely the story we'll be tracking closely as it continues to unfold. So make sure you're subscribed before that verdict finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does Microsoft's high-risk, physics-first bet on genuinely unproven particle physics feel like the kind of bold, visionary gamble that eventually defines an entire industry? Or does IBM's patient, methodical, proven approach feel like the safer, ultimately smarter, long-term strategy? And does NVIDIA's refusal to bet on any single qubit technology strike you as the shrewdest move of this entire hardware war, or a strategy that could collapse entirely the moment one specific competitor finally, decisively pulls ahead of all the others? Leave your honest answer down in the comments below, and as always, I read every single one.